Welcome to Math 201, the lecture on section 2.3. We're going to talk about the derivative function and the limit definition of the derivative. In our last lesson, we defined the derivative of the function f at a specific point, x equals a. So a is a number here, to be f prime of a, which is the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay, that is the algebraic definition. It is the slope of the tangent line to f at a point x equals a. So let's jot that down. This is the slope of the tangent line to f at a specific point x equals a. So it is a number, right? The slope of a line is a number like 2 or 5 or negative a half, right? So f prime of a is a number. We can find an f prime of a for every number a, right? So I can calculate the slope of the tangent line at 5 and 6 and 7 and any number I want, right? So we can think of f prime of x as a function of x. So instead of thinking of this as a specific number, think of it as an x that can take on any number. So x is now a variable, okay? So the derivative of the function y equals f of x at x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So the only difference here is that instead of an a, I have an x in this formula. Okay. The a represented a specific number. It was like 5, right? But the x is a variable that can take on any value. So the result of this calculation is a formula. This is a formula that calculates slope at an x value that you have to input. Okay, so the result of this calculation is a number, and the result of this calculation is a formula with x's in it. Let's see if we can take the graph of y equals f of x, given on the left here, and sketch the graph of y equals f prime of x, the derivative function. So the basic idea when we graph the derivative function is to plot points of the form x comma slope. So at any given x value, from this graph, I want to calculate the slope of the tangent line at that point, and that'll be the y value for my derivative. Okay, so I have x. I'm going to make a table of values down here, x and slope. Okay, so I'm going to find some spots, draw some little tangent lines. The most clear places are places where the tangent line is horizontal. Okay, because a horizontal line has a slope of 0. So those 3 locations are going to have a slope of 0. So it looks like about -1, maybe 1.2, and 3. Okay. Those 3 x values, my slope is 0. And then I can plot the points that as I figure them out in the table, I'm going to plot them in the other picture. So this is going to be x, and my y-axis is representing slopes. Okay, the slope at the x value. So at -1 and 1.2 and 3, my x values, um, those x values give me a slope of 0. Those are where I have horizontal tangent lines on f. Okay, so then let's think about before x equals -1. So like all over here. Okay, so before x equals -1. If I draw some tangent lines in, okay, they are all negative slopes. Okay, they're very steep negative, becoming less and less steep as we approach 0. But I'm going to write negative here, negative slopes. And then from x equals -1 to x equals 1.2. Okay, so all in between the next 2 zeros, I have positive slopes. Okay, and they start out getting steeper and steeper. And then at some point, they start becoming less steep and going back to zero, but they are all positive. Right. And then from 1.2 to 3, so I'm going to draw some tangent lines along here. And these tangent lines all have negative slopes. And then from 3 on, my tangent lines have positive slopes and they are just getting steeper and steeper and steeper. Okay, so let's see if I can fill in my graph with this information. So before -1, my slopes are all negative, and as I move to the left, they get steeper and steeper and steeper. So they start out just a little bit negative, and then they're more and more and more negative. So I'm just going to draw it like going more and more negative. Okay, so these are my y values, or my slopes get more and more negative. Okay, then between -1 and 1.2, oh, whoops, there we go. Between -1 and 1.2, from here to here, I have positive slopes, and they start out close to zero, and they get more and more positive, but then they hit some like peak level of positiveness, and then they start to come back down towards zero. They get less and less steep and approach zero again. So these are positive, they hit some maximum steepness, and then they come back down to zero. Okay. And then between 1.2 and 3, my slopes are negative. So these orange lines, right, they start close to zero and they get more and more steep until they hit some maximum steepness, and then they are still negative, but they come back down towards back up to zero. Okay, so these are negative like that. And then after x equals 3, these blue lines, these all have positive slopes and they just get steeper and steeper and steeper. So this goes up like that. Based on the graphs above, okay, this is f of x and f prime. That's the graph that we just drew together in the previous slide. Based on these graphs, let's guess the degree of f of x. So it looks like a polynomial. It's got both arms up, which means it's an even degree, um, but it's got 3 extrema, which means it can't be quadratic, it has to be at least quartic. Okay, so we're going to guess this is the 4th degree. Okay, and then this uh, this graph, it has one arm down and one arm up in terms of its end behavior. So that means it's got to have an odd degree, um, and it's got 2 extrema, which means it has to be at least 3rd degree. So let's guess 3rd. Oops. Okay. So we will soon see that for any polynomial f of x, the degree of f prime is 1, um, 1 less than the degree of f. Okay. So here, the degree of f we guessed was 4th, and the derivative we guessed was 3rd, and that is in fact always true. When you take the derivative of a polynomial, the degree will decrease by 1. This is the first activity of today's lesson. Please pause the video to work through this activity and then come back to review your work. Okay, go ahead and pause now. Okay, now that you have tried this activity on your own, we can go through it together. So I have a graph here with several points labeled. At which of the points A, B, C, D, E, and F is the particle's instantaneous velocity positive, negative, and zero? It is important that I should have labeled these axes as time and position. So with those axes appropriately labeled, now we can answer the question. Okay, at which of the points A, B, C, D, E, and F is the particle's instantaneous velocity positive, negative, and zero? So remember, instantaneous velocity, um, or instantaneous rate of change, is the slope of a tangent line. Okay, so if I draw a tangent line at each of these points, those slopes tell me the instantaneous velocity. Okay, so I have two places where my instantaneous velocity is 0. Those are the easiest to identify, which is why I usually do them first. Okay, so we have A and C. Both look like horizontal tangent lines. So those are places where the instantaneous velocity is 0. Okay, positive, I want to identify positive slopes. So that would be at B, D is negative, E is negative, and F. So B and F have positive slopes, which means they have positive instantaneous velocity. And what's left are the negative instantaneous velocities at D and E. What is the average velocity of the particle on the interval from 0 to 5? T equals 0 to t equals 5. Okay, so here's t equals 0, here's t equals 5. So if I connect those with a straight line, the slope of that line tells me average velocity over that interval. So the slope of the line connecting A to F is 0. So my average velocity on that interval is 0. Okay, finally, we want to roughly sketch the derivative s prime. I think I might do it on the same set of axes. I don't know. Okay, so maybe not. I will draw some axes here. Okay, so I had tangent lines that were horizontal at A and C. So this is A, B, C. I'm trying to actually line these up. D, E, and then F is way over here. Okay, so I want to sketch the derivative, and I had horizontal tangent lines at A and C. So those are going to be zeros. Okay. And then in between A and C, the slopes are positive, right? We said B was a positive slope, and they start out like just a little bit positive. They hit maximum positiveness at B, and then they come back down to 0. So something like that. And then let's mark this point right here. We'll call that G. This looks sort of halfway between E and F. Okay, so then at C there's 0, and they hit 0 again at G. So let's put that on there. And then between C and G, the slopes are negative, right? Negative, negative, negative. Looks like they hit maximum negativeness maybe around E, maybe a little before, but we'll just call it E. So they get very, very negative, maximum negativeness around E, and then they come back to 0 at G. So something like that. And then from G to F, the slopes are positive again, and they're just getting more and more positive. So something like that. Let's use the limit definition of the derivative to find a formula for the derivative of a line. So remember the formula for a line is mx plus b. So I want to find a formula for f prime of x. So the definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. And then I'm going to use function notation. I'm just going to say this f of x plus h, that means go to your function f and replace all the x's with x plus h's, okay, in the whole formula. So this is going to be the limit as h goes to 0 of m times x plus h plus b minus f of x, which is actually a formula, mx plus b, right? In our previous lecture, this was a number because we would plug a number into f, but now f of x represents a whole formula, mx plus b. So I'm going to use a parentheses here because it's subtraction, and then all over h. So it is important at every step to write your limit as h goes to 0, even though that can get tedious. It's important to make your equal sign true. Okay, so we're going to write the limit at every step. Okay, so next I'm going to distribute my m and distribute my negative sign here. So this is going to be mx plus mh plus b minus mx minus b all over h. And then I can combine like terms, and I have a positive mx and a negative mx, so those cancel. And then I have a positive mh, oops, sorry, didn't mean to do that. I have a positive b and a negative b, so those cancel. So all I'm left with is the limit as h goes to 0 of mh over h. My h's cancel. And this is the limit as h goes to 0 of m. And several lectures ago, we talked about a property of limits, that the limit of a constant is always the constant. So this is m. Okay, similar problem. We are going to use the limit definition of the derivative to find a formula for the derivative of x squared. So the limit definition of the derivative is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, and then I'm going to just use function notation to plug stuff in. So f of x plus h means look at your f of x formula, replace all your x's with x plus h's. So this is going to be x plus h squared minus, that was my f of x plus h, is x plus h squared, minus f of x, which is just the formula x squared all over h. So this is the limit as h goes to 0 of, order of operations says go ahead and square this x plus h. So that's going to give me x squared plus 2xh plus h squared minus x squared all over h. My x squared, I have a positive one and a negative one, so those cancel. And this becomes the limit as h goes to 0 of 2xh plus h squared over h. Okay, at this point, I can't plug in a 0 yet because I get 0 over 0. We don't like division by 0. I can't just plug in this h equals 0. So what I'm going to notice is that my numerator and my denominator, sorry, that both terms of my numerator have an h in them. So I'm going to factor it out, and I can cancel it with the denominator. So this is going to be the limit as h goes to 0 of h times 2x plus h all over h. And then my h's on the top and the bottom cancel. So this is the limit as h goes to 0 of 2x plus h. And now, at this point, I can plug in my h equals 0, and I have no denominator of 0 to worry about. So this just becomes 2x plus 0, which is 2x. This is your second activity of lesson 2.3. Take a few minutes to work through this on your own before you watch the video of me going through this. Go ahead and pause your video now. Okay, now that you've taken a few minutes to work through that on your own, we can do it together. In class, we used the limit definition to compute the derivative of x squared. Now we're going to similarly work with the function x cubed. So state, without simplifying or taking any limits, the definition of f prime of 2. So we're not asking for the limit definition of f prime of x yet, just f prime of 2. So this is a little bit of review from our previous lesson. So f prime of 2 is the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. So this calculates the slope of a secant line from x equals 2 to some point a little to the right of x equals 2, x equals 2 plus h. So this calculates the slope of that secant line, and then when you take the limit as h goes to 0, you get the slope of the tangent line at 2. Now, algebraically, we want to compute the value of the limit in part 1a. So I want to compute this to find f prime of 2. And we might find it helpful to know how to cube a number, right? Because f of x is x cubed. Okay, so when I work on this, I'm always going to write my limits at every step, limit as h goes to 0. So f of 2 plus h, that means look at your formula for f, we're replacing the x's with 2 plus h's. So this is going to be 2 plus h cubed minus f of 2, which is 2 cubed, all over h. So in my next step, I'm going to cube my 2 plus h. So I'm going to use this little formula that they gave me. So in my example, my a is a 2 and my b is an h, and I'm going to plug into this formula. So let's see, a cubed, that would be 2 cubed, which is 8, plus 3a squared b. So a squared would be 2 squared, so that's 4. 3 times 4 is 12, so 12h plus 3ab squared. So it's going to be 3 times 2 times h squared, so 6h squared, plus b cubed, so that's plus h cubed, and then minus the 2 cubed here, which is an 8, all over h. And this will be the limit as h goes to 0. My 8's are going to go away. I have a positive 1 and a negative 1. And I still can't plug in h equals 0 because I get 0 plus 0 plus 0 over 0, right? Still have a division by 0, which I don't like. So instead, I'm going to notice that every term in my numerator has an h in it. So I can factor it out and cancel with the denominator. So this is going to be h times 12 plus 6h plus h squared all over h. My h's cancel. And then when I plug h equals 0 in for the remaining h's, I just get 12. Okay, now I want to use the limit definition to find the derivative function f prime of x. So we just found f prime of 2. The answer was a number, right? Now I want to find f prime of x. The answer should be a formula with x's in it. So f prime of x, the limit definition says the limit as h goes to 0 of f of x plus h minus f of x all over h. So in the previous example, these x's were 2's, okay, which made the answer come out to a number. And now my x's are variables. So my answer is going to have a variable in it. So this is going to be the limit as h goes to 0, f of x plus h. Remember, f of x is x cubed. We're still working on that same function. So f of x plus h is going to be x plus h cubed minus f of x, which is x cubed, all over h. So again, I'm writing my limit at every step. And x plus h cubed, use that same formula that was given in part B to cube x plus h, and you get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I'm done cubing this. Now I have to do minus x cubed all over h. My x cubes cancel. And I still have an h in the denominator. I don't love that because I can't plug in 0 into a denominator. So instead, notice that every term in the numerator has an h. You can factor it out, factor one of them out to cancel with the one in the denominator. We've got the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared all over h. Then my numerator and denominator h's cancel. And finally, I can take the limit as h goes to 0 because I can make this h 0 and this h 0. There's no 0 in a denominator to worry about. So this becomes 3x squared plus 3x times 0 plus 0 squared, which is just 3x squared. Now we're going to use our algebraic skills to tell us something about a graph. We're going to use the general statement for the derivative of a power function, that the derivative of x to the n is nx to the n minus 1. So I'm giving you a formula that you are allowed to use to finish this activity. Find the point where the following quadratic functions have horizontal tangent lines. Okay, so first of all, a tangent line is a derivative. Okay, so I need to know the derivative of each of these before I do anything else. So g prime of x. I'm going to use this secret formula that I was given, that to take the derivative of a power function, you just take the exponent, bring it down in front, reduce the exponent by 1. So the derivative of x squared is 2x. We actually already did that together earlier. And the derivative of 4x is 4, because we also already found the derivative of any mx plus b is just m, right? And then h prime of x is going to be 2x plus 0, because the derivative of constant will be 0. And we have 2x plus 4 and 2x. So I want to know where these have horizontal tangent lines. So a tangent line is a derivative, and a horizontal line has a slope of 0. Okay, so I want to know, where do these derivatives equal 0? Because derivatives are slopes of tangent lines. Where do they equal 0? That's where they'll be horizontal. So I set g prime of x equal to 0, and I'm going to set h prime of x equal to 0, and those will be the locations of my horizontal tangent lines. So 2x plus 4 equals 0, and I get x is negative 2. And h prime of x is 2x equals 0, and I get x is 0. On the axes below, sketch the graphs of the given quadratics. So remember, it was x squared plus 4x. And h of x was just x squared plus 1. Okay, so if I want to graph these, I know they're both quadratics. They're parabolas that open up. I can be a little more specific in that I could find the x-intercepts of g of x by factoring out an x, set it equal to 0, and I get x equals 0 and negative 4 as my x-intercepts. So 0 and negative 4. And then halfway in between, we will hit a vertex. Okay? And if I want to know the y value, I could plug that in, like g of negative 2. That would be negative 2 squared plus 4 times negative 2. So that's 4 minus 8 is negative 4. So negative 2, negative 4 is my vertex, like this. And what you might notice here is that I have a horizontal tangent line right where I expected it to be at negative 2. Now to graph h of x equals x squared plus 1, that's just x squared shifted up 1. So the vertex is going to be about right there, and then it opens up like that. And what you should notice is that there is a horizontal tangent line right where we expected it to be at x equals 0, based on our calculations in the previous question.